Here's a second example. According to the Miniature Earth Project, 12% of the world's population is unable to read. In a random sample of 3,000 adult Americans aged 18 or older, 300 said they were unable to read. What is the population? We can use the problem statement to help us figure this out. If you take the random sample of 3,000, adult Americans aged 18 or older unable to read, and replace the 3,000 with the word all, that's your population. So all adult Americans aged 18 or older unable to read. Now we wish to obtain a point estimate for the proportion of adult Americans aged 18 or older who are unable to read. The point estimate is your best guess of the true proportion for all adult Americans. Our point estimate is p hat. It's the number of successes in the sample out of the sample size. Here we saw that there were 300 adult Americans aged 18 or older and able to read out of a sample of 3,000 adult Americans. This gives us a point estimate equal to 0.1 or 10%. Now let's form the 90% confidence interval for the proportion of Americans aged 18 or older who are unable to read. What we're saying is 0.1 is our best guess, but the true proportion could be a little bit bigger or a little bit smaller than 0.1. So let's give ourselves a margin of error. This margin of error is composed of a z-score, and for 90% confidence, the z-score is 1.645 times the standard error, and the standard error is the square root of p hat times 1 minus p hat divided by the sample size. And it said that we sampled 3,000 American adults. 0.1 minus 1.645 times the standard error gives back 0.09. And 0.1 plus 1.645 times the standard error gives back 0.11. So what we're saying now is that our point estimate is 0.1, but the true proportion could be as small as 9% or as large as 11%. Now, of course, this is only true if our assumptions have been met. And our assumptions are simple random sampling, which we see random sample, so that's been met. 10 or more successes, n times p hat. 10 or more people unable to read. And in this case, 300 people stated that they were unable to read. We also need 10 failures. That's n times 1 minus p hat. You could logic through this though. If 3,000 people were sampled, and out of the 3,000, 300 were unable to read, that means that 2,700 are able to read, which is also a bit larger than 10. So we've met all three assumptions, and we know that this is a valid confidence interval. Based on this confidence interval, is it possible that the proportion of adult Americans aged 18 or older who are unable to read is 12%? To answer this question, you should look to see if 12% is in the confidence interval, and we'll look at it as a decimal 0.12. 0.12 is not a number between 0.09 and 0.11. Since it's not in the confidence interval, it's not likely to equal 12%. It could happen, but it's unlikely. So we will say it is possible, but it is unlikely since 12% is not in the confidence interval. Now that we understand how to create the confidence intervals, let's go over some rules for interpreting them. The general statement should read, we are blank % confident that P, stated in words, is between the upper and lower bound. Remember, confidence intervals are statements about the population proportion. The interpretation should not be about the sample proportion, and the interpretation should not be about individuals. Let's use these rules to write our own interpretation for the confidence interval we just formed. Remember, our 90% confidence interval was 0.09 to 0.11. So to start out, we should say we are 90% confident. So in our interpretation, I've written out that we are 90% confident. The next part says that we should say P in words. P is the proportion of adult Americans aged 18 or older who are unable to read. So far we are 90% confident that the proportion of adult Americans aged 18 or older who are unable to read. And the last part is to state the bounds. We are 90% confident that this proportion P is between 9% and 11%. We are 90% confident that the proportion of adult Americans aged 18 or older who are unable to read is between 9% and 11%. Now that we've written our own interpretation for our confidence interval, let's discuss some of the interpretations below and see what went wrong. You'll need to keep in mind the two rules. Interpretation should not be about sample proportions, and interpretation should not be about individual. Looking at the first one, it says we are 90% confident that between 9% and 11% of these 3,000 adult Americans aged 18 or older are unable to read. When you say 3,000 adult Americans instead of all adult Americans, you're talking about a sample. And we already know that for the sample, 300 out of 3,000 were unable to read. You already know the exact percent, so why give bounds on it? So the problem here is that this statement talks about the sample proportion. In the next statement, it reads that we are 90% confident that the sample proportion of adult Americans aged 18 or older who are unable to read is between 9% and 11%. Again, this statement talks about the sample proportion. It even says the word sample. Instead, it should have read, we are 90% confident that the proportion of all adult Americans. That way it talks about the population proportion. So this one also has the same error. In the third statement, it reads, we are between 9% and 11% confident that 10% of adult Americans aged 18 or older are unable to read. The most obvious one is that the upper and lower bounds were used as a confidence level. The 9% and 11% upper and lower bound were reported as a confidence level. Let's look at the last statement. In 95% of samples of adult Americans aged 18 or older, the proportion who are unable to read is between 9% and 11%. This sentence is trying to use the concept of 95% confidence. 95% confidence means that in repeated sampling, the true proportion would be contained in 95% of the confidence intervals. But saying that 95% of samples would result in confidence intervals of 9% to 11% is wrong. Each confidence interval has its own lower and upper bound. One may run from 9 to 11%, and another could run from 10 to 12%. But either way, there's a little bit of overlap that would allow both of them to contain that true proportion P. So we're not saying that 95% of samples must be stuck between 9 and 11%. Each time you get a sample, the bounds are going to change. So this statement is also incorrect. Here are the works cited used in this lecture.